Hello everybody. In this class, we shall discuss the canonical form of these elliptic equations, and we shall discuss some examples on this kind of equations as well. So, the case that when this b square minus 4ac, this b square minus 4ac is less than 0, in that case, we say that the given partial differential equation is elliptic. And we already proved in these results that if we have an equation like chi is equal to a transformation where chi of x comma y is equal to some constant c1, then from this relation we get the this derivative dy dx. Similarly, if we have another transformation eta is equal to some function of x and y, in that case also, if we have this kind of curve, in this case, if we differentiate it, we get this derivative. So now over here you can check that if b square minus 4ac is less than 0, in that case you see this expression within this under root b square minus 4ac is a negative quantity. That means this dy dx, this kind of quantities would be imaginary quantities. Dy dx would be imaginary, or in other words we can say that this would also be certain imaginary number chi and eta. In fact, they would be imaginary conjugate of each other, complex conjugate of each other. And if this chi becomes is equal to say alpha plus I into beta, and then this, if this eta in that case would be if alpha chi is equal to alpha plus I beta, then its conjugate would be alpha minus I into beta. And in that case you can prove that alpha is equal to chi plus eta by 2, and beta would be is equal to chi minus eta divided by twice I. Now what happens over here? Originally the given partial differential equation was written in terms of the variables, independent variables x and y, and afterwards we were trying to construct a transformation involving chi and eta, but because of this fact that b square minus 4ac less than 0, we find that this chi and eta, both of these two are imaginary numbers or imaginary variables, you can say. Now from this imaginary variable we are again trying to construct certain real variable alpha and then beta. So if chi and eta, these are functions of x and y, in that case we can say that this alpha will also be a function of x and y. Similarly this beta will also be a certain function of x and y. All right, and in that case the given differential equation, which was originally written in terms of x and y, the given differential equation will be now converted in terms of these independent variables alpha and beta, not in terms of chi and eta, because these are all complex valued variables. So over here we can say that alpha and beta, this x and y, are directly transformed to alpha and beta by certain transformation. We shall compute the rule for alpha and beta, and afterwards the total differential equation will be converted into an elliptic differential equation in terms of these final real variables alpha and beta. So chi and eta would be our intermediate complex valued variables. Here, now let us try to understand this problem by the help of certain example. Let me just clear all these notations. Now we consider this kind of example where you see uxx plus x square into uyy is equal to 0. So we actually have over here 1 into uxx. So this 1, this is our capital A. This is our capital A, and uyy, that would be our capital C, and no other term is there. So we can say that capital A is equal to 1, and capital B, this is equal to x square, and no other term is there. Sorry, not capital B, that would be capital C. I made a mistake. Capital C is equal to this x square, this coefficient uyy, that is actually capital C, and no other non-vanishing term is no other non-zero term is there. So we can say that this B is equal to 0. So now you can compute that b square minus 4ac is equal to minus 4x square, and this is minus 4x square is purely a negative quantity. So we can say that this quantity is purely less than 0, and in that case we can conclude that given differential equation is an elliptic partial differential equation. Now we need to convert this given differential equation, into its canonical form. So how to find the canonical form? You see dy dx, if we compute this expression dy dx, uh, we have two different expressions of dy dx, as I discussed in this last case, that this is for the function xi is equal to some constant c1, and this is for eta is equal to c2. So we shall compute this dy dx, these expressions of dy dx. We get that one expression of dy dx is equal to minus I into x, second one is plus I into x. So if we integrate them with respect to x, then on the left, so from this first relation, what we have, we actually have you see dy plus I into x into dx is equal to 0. So if we integrate it, we shall have y plus I was there, yes, I is there. You can, oh sorry, minus I was there, so plus I into x. So it's okay. So now it would be I into x square by 2 is equal to some constant, and if we divide it, we can consider this constant to be equal to I into c2. And if we divide this expression by I, in that case we shall have 1 by I into y plus x square by 2 is equal to c2, and 1 by I, this means minus I into y plus x square by 2. This type of expression is equal to the constant c. So we get one expression minus iy plus x square by 2 is equal to c2. Similarly, if we integrate the second expression, we will get this relation plus iy plus x square by 2 is equal to c1. So these are the expressions of this left hand side. You can see that this left hand side, you can consider this left hand side as the xi function, xi of x comma y. This kind of function, xi is equal to c1, or simply you can write it as xi. So over here xi is a complex valued function, And what is this? This expression would be is equal to eta. Eta of x comma this would be is equal to eta of x comma y, or simply we can designate it by eta. Therefore, its real part. What is the real part? This x square by 2. This is the real part. So this over here you have already we have the expressions of chi and eta. So its real part, that is x square by 2, would be is equal to alpha. That would be alpha, and its imaginary part, that means simply y. Forget about the imaginary number small I. The imaginary coefficient y, only this y would be the quantity beta. So we have alpha is equal to x square by 2, beta is equal to y. So this is the final transformation we have. We actually got the transformation from x, y coordinate system to alpha, beta coordinate system. Got it? We have a transformation from x, y coordinate system to the alpha, beta coordinate system by this kind of transformation formula. And therefore the total partial differential equation has to be written where this alpha and beta, both of these two are independent variables. So the partial differential equation should look like this kind of partial differential equation: a bar into u alpha alpha plus b bar into u alpha beta plus c bar, and so on. So other expressions should also similarly appear: u beta beta, and finally similarly then we have d into this partial derivative u alpha, then after that e into partial derivative u beta, similarly plus f and g and all, etc. So plus a, let me complete the expression, plus f into u is equal to g. Everything has to be written in terms of bar. Okay, so that would be the final partial differential equation. And this a bar and b bar will have this type of expressions. This kind of expressions, and there what we have this kind of expressions. If we compute them, we already know alpha. So what is alpha x? Alpha x, this is our alpha. Alpha is equal to x square by 2. So what is the partial derivative alpha x? Alpha x is equal to x. Similarly, we can compute the remaining other partial derivatives. So we get this expression of capital A and capital A bar, B bar, C bar, D bar, E bar, and F bar, G bar. What we find is that over here only a non-vanishing contribution comes from A bar, then C bar, and D bar. So if we put the values of these three expressions in this partial differential equation, then what we have, this is our A bar into u alpha alpha. Okay, then b bar is equal to 0. So forget about this u alpha beta, this kind of term. Then c bar is equal to x square. So x square into u beta beta, this kind of term comes over here. Now then the non-vanishing term is d bar into u alpha. So d bar is equal to 1. So over here we can write simply 1 into u alpha, that is actually u alpha, and the remaining all these coefficients are equal to 0. So the remaining portion becomes is equal to 0. So in this way we finally write the expression where the independent variable has been taken as alpha and beta. Okay, now over here as we got this expression, Then if we keep this u alpha alpha and u beta beta on the left hand side and the remaining portion on the right hand side, then you see this becomes this Laplacian operator del square u in terms of two variables. So this del square u, that is actually u alpha alpha plus u beta beta, becomes is equal to minus u alpha divided by twice alpha. So this is the final this is the final canonical form of the given partial differential equation, which was given as the elliptic partial differential equation. Okay, so in this way you can convert a given elliptic partial differential equation to its corresponding canonical form. Hmm? Now we discuss one example. This is the example. What does it say? It says that classify and reduce this relation. Relation means it's actually a partial differential equation to a canonical form. Firstly, we have to reduce it into the canonical form and then solve it. Hmm. So let's check over here. If you consider this one, this coefficient, this uxx, that is actually capital A. This is our capital A. Then this x square, that is the coefficient of uyy, that is our capital B. And then minus twice xy, the coefficient of ux, not capital B, sorry. This is capital C. And then this minus twice xy, and that would be our capital B. So if you consider capital A and B and C in this fashion, in that case we can compute that b square minus 4ac becomes is equal to 0. Therefore the given equation is a parabolic differential equation, and we know that in case of parabolic differential equation, dy dx, this dy dx can be written in this fashion, b by twice. So this dy dx, if you put b and twice over here, this becomes is equal to minus x by y. So dy dx is equal to minus x by y. So if you integrate it back over here this can be written as y into dy plus x into dx is equal to 0. Now if we integrate it, we get a relation like x square plus y square is equal to c1. So this left hand side would be the function xi. That's why this xi has been taken as x square plus y square. Now in case of parabolic differential equation, we know that we need to choose one more variable eta, so that the Jacobian is not equal to 0. So whenever we have this type of expression, xi is equal to x square plus y square, over here they have taken eta is equal to one term, y square. You could also take eta is equal to x square. Both of them would be valid transformations. You can check that if you put if you take in place of y square, if you take eta is equal to x square, in that case also the Jacobian of the transformation would be not equal to 0. Anyway, they have taken eta is equal to y square, and so this is the this canonical variables xi and eta. Now in terms of xi and eta, we have to express everything. So we need to compute the coefficients. Over here a bar is this kind of expression. A bar becomes equal to 0. And b bar becomes is equal to 0. One can take the expression of c bar, d bar, e bar, f bar, etc. All of them would be is equal to 0. So only non-vanishing contribution would come from c bar. All right. And what is the term corresponding to c bar? C bar into u eta eta, u eta eta, that would be is equal to 0. This is the only non-vanishing contribution. So if you put the expression of c bar over here, you will get this type of relation. C bar is equal to this 4 x square y square, and as because on the right hand side we have 0, therefore we can simply write this this relation as u eta eta is equal to 0. So if u eta eta is equal to 0, then integrate it once with respect to eta partially, of course. you will get certain expression independent of theta. Maybe it is an expression or a function of xi. So it may be f of xi, where f is an arbitrary function. Now again, if we integrate it with respect to eta again, in that case it would be f of xi multiplied by eta plus one more quantity which is independent of eta, that is constant with respect to eta. So it would be xi of g of g of xi. G may be any arbitrary function. Got it? So this is the expression u is equal to f of xi into eta plus g of xi. So if we just put the expressions of xi and eta, xi is equal to x square y square. So we put xi is equal to x square y square, and what is eta? Eta is equal to this kind of y square. We have taken eta is equal to y square over here. This is eta is equal to y square. So in this way, we get the final solution of the given partial differential equation, where f and g are two arbitrary functions. Okay, this is one example that I wanted to discuss. Now, if you look at this second example, over here, this b square minus 4ac is negative. These are the coefficient. This is our capital A. This is our capital B, and not capital B, capital C. This is our capital C. The coefficient of UIY. This is our capital A. And what about B? You see, no term is there like UXY. Therefore, we can say that capital B is equal to 0. Therefore, by this kind of values of capital A, B, and C, we get that b square minus 4ac is less than 0. Okay. So it is an elliptic differential equation, and over here you can observe that dy dx becomes some imaginary quantity. So if we integrate them back, we will get this type of relation. This is the first relation, and this is the second relation. You can check that both of them are complex conjugate of each other. And the real part, this is the real part. So this real part should be taken as alpha, and this is the imaginary part. Forget about this I. So this is the imaginary part, and this imaginary part should be taken as beta. So in this way, we get the transformation of alpha and beta, and finally we can compute the coefficients a bar, b bar, c bar, etc. And whenever we put these expressions of a bar, b bar, and c bar, we finally get this kind of canonical form. We will have to elaborate this portion, because you see these are very briefly written in this book, but you will have to elaborate at least in exam. So in this way, we get the canonical required canonical form of the given differential equation. Now let's consider another example. You see, it's a bit difficult, or you can say not difficult. Actually, two cases arises over here. Over here, you see 1 into x square. So this capital A is equal to this 1. And uyy is there, uyy. So this is our capital C, and no term like uxy is there. So we can say that capital B is equal to 0. With these values of capital A, B, and C, if we compute b square minus 4ac, then this b square minus 4ac becomes equal to minus 4x only. Minus 4x only. So it may be positive, may be negative. This, depending upon the sign of x, this minus 4x may be positive, may be negative. And therefore, if it is negative, then it becomes a hyperbolic differential equation. Sorry, if it is negative, it becomes an elliptic differential equation, and if it is positive, then it becomes a hyperbolic differential equation. So you see, if x is greater than 0, then this minus 4x is less than 0. So that in that case, this given differential equation becomes an elliptic differential equation. Again, if x is negative, if x is a negative quantity, then this minus 4x becomes greater than greater than 0. So in that case, it becomes a hyperbolic partial differential. That's why we have to discuss the differential equation into two cases. In this half plane x less than 0, we have to use the treatment of hyperbolic differential equation. Over here you see they have taken root over of minus x, root over of minus x. Over here x is negative, therefore minus x is positive, therefore this is a valid expression, a real valid expression, real expression. Okay. So over here we have computed dy dx. Dy dx is equal to minus of root over of minus x, and for the second expression, this dy dx is equal to plus root over of minus x. So if we integrate them, then what we get this type of expression. This is the first expression: y is equal to 2 by 3 minus x to the power of 3 by 2. So from this expression, if you write it in this way, y minus of 2 by 3 minus x to the power of 3 by 2 is equal to c1. You see, you get the expression of the variable xi. But over here you can also write this expression. You see, this is the expression of xi. Now you see over here you can also write this expression over here, just in order to get this, in order to get rid of this 3 by 2. One can start with y minus 2 by 3 minus x to the power of 3 by 2, like this, is equal to the constant c1 or c2, whatever you call it. Maybe the constant c1. But over here you see, forget about the constant for the timing, just forget about this constant. In that case, this would be the expression, this is equal to 0, the expression, or in other words, y is equal to 2 by 3 into minus x to the power of 3 by 2, that would be the expression. Now in order to make the calculation simple, we are taking the square of both sides. Okay. And what we have, we should write this kind of square over here, not like this, y square should come. So y square, and then what we get, 3 by 2 is equal to minus x whole cube. Either you consider this kind of expression, and then if you write this, or you shift this expression, that 3 by 2 y square minus x cube. If you consider xi is equal to this, then it would be a correct expression. Or we can simply choose y just from this expression. We can simply choose the expression of xi and eta. In that case, these derivatives, this kind of derivatives, would be a bit complicated derivatives. That's so. In this way, they have computed they have taken the variables xi and eta. These are some tricks that they have used. Anyway, so in this way, with these expressions of xi and eta, we got the expression of a bar, then b bar, then c bar, then d bar, e bar, f bar, etc., f bar, g bar, etc. And finally, we got this kind of canonical form of the given partial differential equation. U xi eta is there, so it is in parabolic form. No, not parabolic form, sorry, it is in hyperbolic partial differential equation, hyperbolic partial differential equation. Now we have to consider the case when x is greater than 0, this case number 2, for elliptic, whenever this differential equation becomes elliptic. So this is the case number 2. In that case, you see dy dx becomes imaginary. So if we integrate them, we get this kind of expression. Again, some mistake is there. If you integrate them, you see if you integrate this first expression, this kind of expression dy dx, if we integrate it, we actually have dy is equal to I into root over of x dx. So if we integrate it, we will get y is equal to I into x to the power of 3 by 2. Over here we will have 2 by 3 plus 0 or plus some constant c. So forget about this c for the time being. You forget about this c. So because this c does not have any contribution in the determination of xi and eta. So if we make the square on both sides, what we shall have y squared, and this 2 by 3 is equal to 4 by 9. So be a little bit careful about this kind of expressions. And there we get this kind of expression. I square would be is equal to this minus 1, and x cube is there. So you see we actually got this wrong expression over here. You need to get correct expression. So but over here my advice is to stick to with this kind of expression. Don't make square, because in that case this I square would become real, and in that case problem may arise. So my advice would be to take this xi is equal to this y minus I into 2 by 3 into x to the power of 3 by 2. This may be xi, and eta can be written as y plus this I into 2 by 3 into x to the power of 3 by 2. This is my advice. Don't make it complicated. So that this real part would be is equal to alpha, and this imaginary part 2 by 3 into x to the power of 3 by 2 would be is equal to beta. So in this way we can compute the expressions of alpha and beta, and finally by this kind of computational process we can convert the given partial differential equation into its corresponding canonical form or normal form. So these are few examples that I want to discuss today, and some computational complication is there in this kind of expression. Some mistakes are also there, so you have to be little careful whenever you go through these examples. So that's all for this lecture. Thank you for being with us.